This is a production of the Chemical Education Material Study.
There are many possible ways to assemble the various parts needed to form a car. The system of steps actually used is called the mechanism. Parts come together in a series of mechanistic steps. Products form. Any chemical reaction also proceeds by a series of mechanistic steps. But molecules are hard to see. How do we discover chemical mechanisms? Here is a common chemical reaction, the hydrolysis of an ester. We cannot see the molecules react, yet chemists know a great deal about the mechanism of the reaction. Chemists believe that hydroxide ion must collide with the ester to give this intermediate, which then decomposes into products. But how did we learn that this is a likely mechanism?
Well, first we need to know the starting materials. Methylbenzoate is one, the methyl ester of benzoic acid. Let's measure out some of the ester. We then add it to the flask in which we will carry out the reaction. One reactant is then methylbenzoate. The second reactant is a water solution of sodium hydroxide. It too is measured. The sodium hydroxide is then added to the reaction flask. Note that the two reactants do not mix readily. An electric heater is placed around the flask and the stirrer started to ensure even heating. Prior experiments have shown that a temperature of about 80 degrees is desirable. Since the reactants are almost insoluble in one another, they form two liquid layers. In order for the rate of reaction to be appreciable, we must mix the reactants by increasing the stirring rate. The cloudiness indicates the presence of tiny droplets of ester suspended in the water solution. The droplets give a large area of contact between the water and the ester, and the rate increases. After 3 minutes of reaction, the contents have begun to clear. The final clearing means that a homogeneous solution has been formed. The ester droplets have disappeared. The hydrolysis appears complete.
Let's isolate the products from this solution. We add a boiling chip to the reaction vessel and prepare to distill the contents. We distill through a column filled with a metal packing. And find that a constant temperature of 63 degrees Celsius is reached. Under these conditions, a colorless liquid condenses and drips into a graduated cylinder. Identification of its boiling point and other properties prove that it is methanol. The other product is still in the hydroxide solution. We will now acidify the basic solution. Addition of a strong acid causes precipitation. The solid proves to be benzoic acid. Careful measurement of the amount of acid added would show that the amount of hydroxide ion was not changed by the reaction. Hydroxide ion was a catalyst. The benzoic acid is filtered from the solution. We wash the benzoic acid to free it from excess solution, then dry it.
Quantitative measurements of the dry benzoic acid and the methanol show that 1 mole of benzoic acid and 1 mole of methanol are formed when 1 mole of methylbenzoate reacts. Hydroxide ion was a catalyst. The net reaction then is methylbenzoate plus water gives benzoic acid plus methanol. To investigate possible mechanisms for this reaction, let us use a molecular representation of the net reaction. As we compare the reactants to the products, we see that much of the original structure has been retained. For instance, the benzene ring with its adjoining carbonyl group has transferred intact. Similarly, the methyl group, CH3, has also remained unchanged. But what about the other oxygen atom? Let's examine the possibilities. This oxygen atom in the methylbenzoate could end up in the alcohol molecule by remaining attached to the methyl group. If this happens, the oxygen from the water would end up in the acid molecule.
Here is another possibility. This oxygen could end up in the acid molecule by staying with the benzene ring. In this case, the water would supply the oxygen for the alcohol. So there is 1 oxygen atom in the ester whose fate we do not know. What we need is some way to label this oxygen atom, which we will call the bridge atom, so we can follow its path in the reaction. Fortunately, there is a way to prepare such an ester with a labeled oxygen atom, oxygen 18, in the bridge position. The most common oxygen atom, oxygen 16, has an atomic mass of 16 with 8 protons and 8 neutrons in the nucleus. But many elements have more than 1 stable isotope. Oxygen 18 is also a naturally occurring stable isotope with 8 protons and 10 neutrons in its nucleus. The 2 atoms are chemically similar, but differ in mass.
Ordinary oxygen compounds contain only 0.2% oxygen 18. But here is a specially prepared sample of water, 10% of whose oxygen atoms are oxygen 18. Using this as our starting material, we can synthesize an ester in which 10% of the bridge oxygen atoms are the heavy isotope, oxygen 18. In the first step of our reaction, the labeled water reacts with sodium. This forms hydrogen and labeled sodium hydroxide. The labeled sodium hydroxide is then added to methyl iodide. This forms sodium iodide and labeled methanol. Finally, the labeled methanol reacts with benzoyl chloride to form hydrochloric acid and labeled methylbenzoate. This synthesis gives us a sample of methylbenzoate labeled in the bridge position.
This mass spectrometer will detect the oxygen isotopes in water. First, a flask containing some ordinary water is connected to a vacuum system and the air pumped out. Water vapor from the flask is introduced into the spectrometer where it is ionized and passed through a combination of varying electrical and magnetic fields, then strikes the detector. An electrical impulse from the detector is transmitted to this pen, which moves to the right when ions of each mass strike the detector. The more ions that strike the detector, the further the pen moves to the right. At this mass, a small number of ions struck the detector. This large response must represent a very common kind of ion striking the detector. Here's the chart from ordinary water. There are 3 peaks of mass 16 oxygen ions, mass 17 OH ions, and mass 18 ordinary water ions.
Now let's try the water enriched in oxygen 18. Here's the O16 peak. Then the peak due to OH of mass 17. And the big peak due to ordinary water of mass 18. But look, here's something else at mass 19. And again something else at mass 20. Comparison of the peak heights due to the ions containing oxygen 16 with the smaller peaks due to oxygen 18 ions confirms that the sample of water indeed contains 10% oxygen 18.
Now let's check the presumably labeled ester. We use a mass spectrometer which can handle molecules of heavier mass than we've used so far. The ester has been placed directly into the mass spectrometer. The large ester molecule will break into many smaller fragments, but we shall find them easy to identify. Here is the printout. The peak at mass 136 is from ions of the ester containing oxygen 16. That at 105, 31 mass units less, is from ester ions that have decomposed, losing CH3O, with oxygen 16, the bridge oxygen. The peak at 77 is from ions that have further lost the CO group. Now note the small peak at mass 138. About 10% of the height of the 136 peak. The 138 peak is from ions where oxygen 18 has replaced one of the oxygen 16s. The absence of any peak at 107, which would have come had the bridge been oxygen 16, proves the oxygen 18 was the bridge oxygen as we planned.
Therefore, we conclude that we now have an ester with labeled oxygen 18 here in the bridge. With this labeled ester, we are ready to repeat our original hydrolysis. But first, let's review the possible fate of our oxygen atom. You remember it could end up in the acid molecule. Or it could end up in the alcohol molecule. Now let's perform the hydrolysis and see where it does go. The hydrolysis is performed in the same manner as before, but using the labeled ester. The reactants are placed in the flask, which is stirred and heated. The product is distilled to give methanol. Does the methanol contain the oxygen 18? Conversion to carbon monoxide and use of the mass spectrometer gives 2 peaks. That's conclusive. The methanol does contain oxygen 18.
What about the benzoic acid? The product is washed and filtered, then dried, and run in the spectrometer, which handles higher masses. We find a high peak at 122, the mass of benzoic acid with oxygen 16. But there is no peak at 124, so no detectable oxygen 18. The acid does not contain the labeled oxygen 18.
We have experimental proof that the labeled bridge oxygen, originally in the methyl ester, goes into the methanol and not into the acid. Thus, the oxygen in the water must have gone into the acid. So we know the fate of each atom in the ester. We will use this information to decide which bonds must break during the reaction. Remember, our end products are benzoic acid and methanol. Let us compare these with our original ester. Notice that this entire group, including the oxygen, remains intact. We assume, therefore, that these bonds are not broken. Our experiment with the labeled oxygen also showed that this group remained intact. Thus, it was not this bond which broke, but must have been this one. But under what conditions did it break? And why was it this bond? Now we recall that hydroxide ion was a catalyst. Let's assume that the hydroxide ion initiates the reaction by attacking the methylbenzoate ester to form this intermediate molecule. The intermediate molecule then decomposes, giving us methoxide ion. Note that the labeled oxygen is attached to the methyl group. Methoxide ion is a strong base and, in the presence of water, will accept a proton from water, regenerating hydroxide ion and forming labeled methanol. So we have discovered a mechanism which is consistent with the location of the oxygen 18 in the labeled methanol. But is the mechanism consistent with what we know about the nature of bond polarity? The ester is an electrically neutral molecule, but within the molecule there are polar bonds. For example, this carbon-oxygen interaction gives this carbon a slight positive charge. This carbon-oxygen bond further increases the slight positive charge. So we see that the attack of the negative hydroxide ion on the positive carbon atom is consistent with what we know about bond polarity. Now we have proposed a mechanism that is consistent with what we know about the reaction. Let's devise an experiment which will further test our assumptions.
Suppose we have an ester that is just like methylbenzoate, except that it has a methyl group substituted on each side of the ester group. These additional methyl groups would not appreciably alter the polarity of the carbon atom to which the hydroxide ion attaches. Therefore, we might expect this ester to react in a manner identical with the original ester. You recall that our proposed mechanism involves the hydroxide ion forming an intermediate molecule, but the bulky methyl groups interfere. The intermediate molecule is difficult to form. Reaction should seldom occur. If our proposed mechanism is correct, the hydrolysis of this new ester, methyl 2,6-dimethylbenzoate, should be much slower than the hydrolysis of the original ester. We'll test this idea by heating the new ester, methyl 2,6-dimethylbenzoate, in the presence of aqueous sodium hydroxide, repeating the original conditions. After stirring and heating for 8 hours, no detectable reaction has occurred. There are still 2 layers, so this experiment further confirms our proposed mechanism.
Since no other suggested mechanism fits all our observations, we assume the proposed mechanism is the true one. Seemingly, these bulky methyl groups have greatly hindered the reaction. The steps we have followed of knowing the reactants and determining the products, exploring the path of each atom involved, checking our suggested mechanism against known bond polarities, and exploring the effect of structure on the reaction are typical of the methods used in determining reaction mechanisms.
Sometimes direct observations provide suggestions about a chemical mechanism. Here we have gaseous hydrogen and oxygen burning to form gaseous water. Clearly, there are at least 3 steps, each taking place in one of the obvious zones in the flame. Actually, there are at least a dozen steps, and their relationship is so complicated that no one knows exactly how hydrogen actually reacts with oxygen. One generalization is fairly good. Most mechanistic steps involve 2 particles colliding and the ultimate formation of 2 new particles. Steps are simple. Mechanisms are not.